4, you take the lithium out, and that's around 4 volts. With LTO, the stoichiometry is lithium 4/3, titanium 5/3 O4.
So it's a spinel. It's a spinel
Yes,
structure.
yes, it's a spinel structure. But with that material, you don't remove the lithium. You add more. So with LiMn2O4, if you add lithium to that, it will go in about 2.8 volts and come out around 4 volts. If you take Li4/3 Ti5/3 O4 and try to remove lithium, it won't come out within the voltage range accessible. So it's a different story because you're kind of adding from half filled, if you like. The voltage is still lower, a lot lower than the other ones. But as an example, if you take lithium nickel oxide and fill it all the way to the normal point and then add more, you can go to lithium 2 nickel oxide, and that plateau is at 1.8 volts, not so different than LTO.
I see. So for this LTO structure, there has already been lithium inside. That's why the intercalation voltage is relatively low. You're adding more lithium to the structure that already have been lithium filled to some extent.
It's part of the reason. It's part of the reason. Okay. If you wanted to compare it with LiMn2O4, adding more lithium, that's 2.8 volts, and the titanium case is 1.5 volts. So there's quite a big difference there, which comes about because of the differences in the transition metals and the electronic structure. Anyway, I don't have a really great answer other than that sort of hand waving. Okay, but it's time to start class, so I'll do that.
Okay.
Okay, so I think everybody should see my screen. Is that true?
Yes.
Yeah. Okay, great. Okay, so I suspect many people will be very happy for this lecture. And maybe many of you would have thought this is what the class should have been like from the very beginning. So here we're sort of talking about real stuff, okay? And at the very outset of class, I emailed you a chapter from the Handbook of Batteries, which covers a lot of the things I'll talk about today, except the cell spreadsheet model, which is at the end of the lecture. So the really important thing about lithium-ion batteries is they're selected to have the positive electrode, which is stable in the air. So if you look at this binding energy diagram, lithium cobalt oxide is stable in the air. It's down below the air stability limit. And the graphite is empty. It has no lithium. So it's also stable in the air, right? And this is key. You want to be able to make lithium-ion batteries in the open air. Now, when you start talking about lithium nickel oxide, if Inez is on the call, she'll tell you it's virtually, almost not stable in the air. It slowly reacts with moisture in the air and ion exchanges, the lithium ion exchanges with protons and makes lithium hydroxide. So, you get very close to the air stability line, and then you have to be very careful about how you handle materials. But in general, you have 2 air stable materials that you're working with when the cell is assembled. And virtually everyone knows the construction of a cylindrical cell. It has a positive electrode or a cathode, which has electrode coatings on both sides of an aluminum foil. It has a separator, which we'll talk about in detail what they are. It has a negative electrode, which is graphite coated on both sides of a copper foil, and another separator, and we'll talk about in detail what those are. And it's wound up into a spiral, a jelly roll, and put into a can. In our laboratory, we make coin cells, and in Mark Overbach's laboratory, they make coin cells, which have A working electrode, say it's the positive, and a counter electrode, which could be lithium metal or graphite if you're making a lithium ion cell, and a separator, and then some parts to apply pressure on this electrode stack. And this is called a coin cell because it looks like a coin. So within lithium ion cells, there are some interesting devices, okay? So in the header of every cell, there's something called a current interrupt device. And what happens to the current interrupt device is when gas pressure builds up in the cell to a significant amount, the header flexes and a current path is interrupted. There's also in some cells something called a positive temperature coefficient fuse. So this is a device that when it gets heated over about 70 degrees C, its resistance becomes very large, and it's reversible. Once the cell cools down, its resistance becomes small again. So this is to protect against cell overheating in a short circuit type of environment where you short the cell, large currents flow, the PTC heats up, becomes high resistance, stops the current flow. And then finally, all these cells, you're not sure which end it's in, it could be in the other end, they'll have a safety vent so that if gas pressures become very large, the cell vent opens and gases and sometimes some smoke and maybe even some flame will come out the safety vent. Now, over time, to limit cell weight and cost, the thickness of the material that's used in the metal can of the cylindrical cell has become thinner and thinner. And sometimes it's possible, although not desired, for cells to rupture out the side. That's called side rupture. And side ruptures is generally very bad because if you have cells stacked vertically side by side, so the cell you see here is in vertical position, put another one next to it. If one has side rupture into the other, you have enormous heat that's blasting at the neighboring cell, and you can set that one off. So you really want cells to vent from the safety vent, and you don't want anything else in the way, so that if one cell vents, it's unlikely to cause propagation to the next. So when you look at modern lithium ion cells and you take them apart carefully, you'll be able to see all the safety features designed into the cell header. Any questions about this? Okay, so electrode making is quite simple. Many people in our laboratory have done this. You take the positive or negative electrode material, you add it to a liquid, and then you add a dissolved binder into that liquid, and usually some carbon black for conducting additive. You mix it together to form what's called a slurry, which is just an intimate mixture of the electrode powder, the dissolved binder, the carbon black in the liquid. And in our lab, we just use a spreader bar to pull across this puddle, and you get a stripe, and you let that dry, and you have a small piece of electrode that you can punch electrodes from. This is a relatively old photograph of an industrial coater from Hirano. This one was using a 60 centimeter wide foil and moving somewhere between 2 and 20 meters per minute. Nowadays, the big coaters will run 1.5 meter wide foil and 10 meters per minute or so. And because you're running so fast, such a wide foil, the drying tunnel, what you coat at one end, It goes through a drying tunnel, and when it comes out the other end, the electrode has to be dry because you're going to wind it up on a take-up spool. The drying tunnels can be really long, like 70 meters even, incredible long. So the thing can run at very high speed. So you can imagine if the foil ever breaks, how fun it is to rethread the machine. So there are some people in the class from Novonix, and Novonix has a coater. It's a little bit shorter in length than this one, but it's a full-blown coating machine for lithium-ion battery electrodes, and you know, they can tell you more about it. We, in the non-COVID times, we would take a field trip out to Novonix to see their lithium-ion coaters and winders and all the cell assembly equipment that they have, but this year we won't be doing that because of COVID. Electrodes for pouch cells and cylindrical cells are often patch coated. So what that means is you have coating for a while, and then the coating head lifts, and there's a bare foil part. You need this bare foil to be able to attach electrode tabs. Now, in the old days when I worked in industry, this was 1988 to 1990 at Mali Energy, the coaters couldn't do this patch coating stuff. And what we had to do was clean a small amount of the foil to make a point where you could weld tabs. Well, cleaning the foil was done with a brush, not too aggressive. You didn't want to damage the foil. But still, you can imagine you're brushing this electrode powder with a brush, you get dust all over the place, and you have a vacuum nozzle there sucking up the dust. But some of that dust in principle could end up lying on top of the electrode if you don't get all of it. And those dust particles could cause penetration through the very thin separators, leading to safety issues. So nobody cleans electrodes now. They're all patch coated. Nobody brushes stuff away. And if they do, they're fools, okay? They're total fools. You just can't do it. And the other thing is, a modern electrode today, if it's done well, you can't brush it off. It's just too well adhered to the current collector, okay? Electrodes are coated on both sides. Some machines can do the coating of both sides simultaneously. Other machines coat one side and then you feed it back to the beginning and coat the other side. Any questions about this at the moment? I thought I heard somebody about to ask a question. Apparently not.
How exactly does the skip coating process work? How do you ensure that there is no uniformity issues in the coating on the in the middle part of the coating versus the sides?
Yeah, well, if you take our pouch cells, which are patch coated, and you examine the thickness right near the beginning of the initiation here, and then right at the very end, the termination there, and in the middle, you'll find out it's not perfect. Getting it to start and end exactly as you want is really pretty difficult. And it's all about the way the coating head is lifted from the foil and the coating stopped and started. I'm not an expert on that, but that's a really tough thing to get absolutely perfect. So if you were asking the question to some of the coating experts at Novonix, they could give you, you know, some good guidance there.
Thank you.
And actually, in years past, I've given a homework problem where everybody gets a real pouch cell, and they have to do very careful measurements of it. But with COVID, there's no way for me to hand those out to everyone. So that homework problem will not exist. So lithium-ion battery cell manufacturing, it's all about packing as much material as you possibly can into the battery can or into the battery pouch. The more you can pack in, the larger energy density you're going to get. And because of this, the electrodes that you coat are compressed to be as thin as possible, okay? And to do this, massive pressures are applied to the electrodes. So this is a funny photograph here. So over in the bottom left is the set of compression rollers we use in our laboratory to compress electrodes. The rollers are about 75 millimeters or 3 inches in diameter, roughly. This is a set of compression rollers that's, I would say, relatively small on an industrial scale, but quite large. And here the rollers are maybe 15 to 18 inches in diameter. Now, where was this photograph taken? You can see me here. This was at the China International Battery Fair in Shenzhen, China. There's a conference center there. It's about the size of 4 football fields. And in that conference center, the vendors brought their equipment, even equipment like this that weighs several tons. Like these rolls weigh several tons. They bought coating machines 50 meters long. There is no equivalent exhibition that takes place in North America and probably in Europe, where vendors bring this large scale equipment that you can really look at. And this was the first time I went to a China International Battery Fair. And when I left there, I just said, you know, North America is so far behind in the whole lithium-ion battery race. It's unbelievable. It's unbelievable. It was a real eye-opening experience. Anyway, so this is a set of experiments done by Thomas Marks. He was a undergraduate student in our laboratory at one point. And what he is showing here is what the density. Yes. Yeah.
Oh, sorry, the slide was lagging, but I see it now.
Oh, sorry. Anyway, this is a photograph from Thomas Marks, and it shows what the electrode density is as a function of the applied pressure on the electrode. So this is in atmospheres of pressure. So after coating, the density is around 1.5 grams per cc. And this is an electrode recipe that has 86% active material. It was NMC 111, 7% PVDF binder, and 7% carbon black. And you can see that when you compress the electrode, it gets thicker and thicker. And these denser and denser, not thicker and thicker. And these numbers that you see here are the initial thicknesses of the electrode coatings. So they were all compressed to roughly the same density, independent of the initial thickness. And then you can see what happens if you increase the active material fraction. So down here, we're talking 96% active material, 2% carbon black, and 2% binder. And as you move to a more electrode that's more higher active material fraction, you can attain greater density. So here, with our equipment, you can obtain about 3.3, roughly 3.3 grams per centimeter cubed. And that allows you to pack more material into the cell, and that's going to give you a greater energy density. So what does it mean relative to the electrode porosity? NMC 111 has a crystal density around 4.7. So if you just worry about the electrode material only, the filling fraction would be 3.3 divided by 4.7. And the porosity would be 1 minus 3.3 divided by 4.7. But the carbon black and the binder each take up some space. So the porosities in these kind of heavily compressed electrodes are somewhere around 25% or so. The pouch cells that we get from Li-Fun, typically the positive electrode compression is around the same place, around 3.3 grams per centimeter cube, just for your interest. Now let's talk about separators. So when I started working in lithium-ion batteries, there were only two kinds of separators you could get, polyethylene or polypropylene. And these are top-down SEM photos of a polyethylene and a polypropylene separator on the top. The holes that you see, there are no scale bars, sorry about that. The holes in the polypropylene separator here are about 400 nanometers, excuse me, 40 nanometers in size, so they're quite small. And if you look at this polypropylene separator, you might say, wait a minute, it looks weird. It looks like it's been stretched from the top to the bottom of the page. It looks like it's been stretched in one direction. And that's the way the pores are made in these polypropylene separators by Celgard. I don't want to go exactly into the manufacturing process, but it's this stretching process that creates this these pores and the way that it looks one-dimensional like this. Whereas the polyethylene looks completely different, as you can tell. And then later on, it became common to build this tri-layer with polypropylene on the outside, polyethylene in the middle, and polypropylene on the outside again. And you might wonder, why is this structure the way it is? So to understand that, you have to know the melting points of polypropylene and polyethylene. Polyethylene melts at 130 degrees C. Polypropylene melts around 155 degrees C. So if you have a lithium-ion cell with a polyethylene only separator, and that cell gets heated to 130 degrees or so, the polyethylene separator will melt, and it might shrink. And if it shrinks, the electrodes will touch, and you'll have a safety problem. All right. So you might say, okay, what advantage does having a tri-layer have over polypropylene? Because polypropylene won't melt and shrink until 155. Well, there's another reason that we're going to come to in a minute that explains why this tri-layer structure is important. I won't talk about it now until we get to that slide. But shrinkage is a big issue. You don't want separators to shrink when they melt, because then the electrodes can come into contact. Here we are. We're at the reason. We're at this topic. So this is a schematic of what happens if an 18650 size lithium-ion cell is put into an external short circuit condition. So initially the current's 0 and the temperature's at room temperature, and then you short the positive and the negative together with a thick wire. The typical 1860 650 cell will deliver 50 amps. Oh, some of you may not know what this means. It means 18 millimeter diameter and 65 millimeter length. It's about the size of your index finger. It'll deliver 50 amps for a brief period of time. The temperature of the cell will start to rise. The current will drop, but it'll plateau around 25 amps. And then it'll go along and it'll go along. The temperature will go up and up and up, and then all of a sudden the current will stop. So the first time I saw this at Mali Energy, I thought to myself, oh, well, I guess the cell's completely discharged. But when you integrate under this current time curve, you learn that only about 1/3 of the capacity of the cell has been discharged. So why did the current stop? The current stops because the polymer separator melts and the pores within it close. That's called shutdown. All right. So the shutdown feature of a separator is really important. So a polyethylene separator will shut down at 130 degrees C, and it will also lose dimensional stability at the same time. If you make this tri-layer, then you're in business, because the polyethylene will shut down at 130. The current in the cell will stop. The electrical current that's driving the temperature increase will stop. And the polypropylene, will have dimensional stability and prevent the short circuiting of electrode to electrode. So for many years, this tri-layer design was the cat's ass, if you will, for making lithium-ion cells relatively safe. Does anyone have any questions about shutdown?
Yeah, question. The polypropylene you said starts melting around 150.
Yes.
So I mean that's not a huge melting temperature difference between the PE and the PP, right?
That's correct. But for many types of cell chemistries, it's enough, because you can see what happens to the temperature once you have shutdown. The temperature doesn't keep going up if you have a cell with electrodes that are stable in the electrolyte at this temperature. Now that statement is hard to say is true when you have high nickel materials in your cell.
Got it.
But the questioner, I think it was Eric, is correct. It's not a very big temperature difference. So people decided we need to do better. And what we have now as state-of-the-art separators go beyond what I've just told you about. So if you take an SEM photograph of a state-of-the-art separator, so this is a cell separator taken from an LG phone. It was a 3.0 amp hour pouch cell. And the side of the separator touching the positive looked like this. You can see polymer, but you can also see this ceramic. And by X-ray diffraction, the ceramic turned out to be aluminum oxide. And you can see the scale of it. There's a 5 micron scale bar, and you can see this aluminum oxide just kind of everywhere where the polymer is. And at the negative electrode side, it looks just the same. And then if you take a cross section of this thing, what you see is this aluminum oxide layer, and there's some polymer in this layer to keep it from falling off. And then you have the polyethylene in the middle, and then another ceramic layer on the outside. So now you've got a situation where the polyethylene gives you shutdown. The ceramic is tightly packed. It doesn't allow the separator to shrink. And in addition, the electrodes will never touch because you have these ceramic layers in between. So these kind of ceramic coated separators became incredibly popular once lithium-ion cells, big ones, started to go into automotive. So large pouch cells, 30 amp hour, 50 amp hour, they all have ceramic coated separators in them to give you, extra safety protection. And this turn of events, this introduction of ceramic coated separators really improved the safety of lithium-ion cells a lot. It was a really big deal.
Hi, Jeff.
Yeah.
I have a quick question.
Yeah.
So once these pores in the P shut down during the once the temperature is higher than 130 degrees C, does this pore shutting down also prevent the transition metal from transporting through? Also, during the normal operations, when the lithium ions can transport through the pores, I think is there any way that also prevent the transition metal to transport through, except for the lithium ions?
No, the transition metals can penetrate through this separator because the electrolyte is going everywhere. So as long as the pores in the separators are not closed, the electrolyte can travel nicely. The ions in the electrolyte can travel nicely through here. The electrolyte is everywhere inside. But once the polymer shuts down, nothing can pass from one side to the other anymore.
Okay, but like during the normal operation, does the transition metal ions are larger than the lithium ions? Would it be possible to make the pores a little bit small so only the lithium ions can transport through, but the transition metal ions cannot?
Well,
Probably
the pores would have to be incredibly tiny at that point, right? You're talking about angstrom-sized pores, and that would just lead to terrible transport properties. The ionic resistance to the separator would be terrible.
Okay, thanks.
Here's a different modern separator. This is taken from a Samsung phone, and you can see in this case they have ceramic that touches the positive side and polymer only that touches the negative side. Okay, and this ceramic turned out to be aluminum oxyhydroxide. It's called Boehmite. It's very commonly used as a ceramic on ceramic coated separators. This is a polyethylene separator, and this is a 4.4 volt cell. So why do they have the ceramic touching the positive? The answer is the polyethylene will react with the positive electrode at these kind of voltages at high temperature. So you have to prevent separator oxidation if you're going to these kind of voltages. So if you use a ceramic coated separator with just one side coating, you put it against the positive. So we have not taken careful SEM photographs of the separators in our LiFeOn cells for some time. We just specify ceramic coated and the ceramic touching the positive side. But it would be very nice just to see what they look like at this state of time. So if somebody wants to do that, that would be a good thing. It would be fun. It is worth noting that at this point in time, there's some pretty serious litigation going on in the space of ceramic coating separators. LG Chem, CellGuard are in a big battle over IP. Who invented this first and who should be being paid royalties over this whole thing. And it'll be interesting to see where that goes. All right, so now I want to talk about what's called the cell spreadsheet model. And the idea here is to use realistic cell parameters to calculate the capacity of an 18650 cell design and make a simple model of a real lithium-ion cell that can be easily handled by anybody, okay? And in the homework, you'll get to go through this yourself. So there's 7 topics that we have to talk about, and each of them will come up on the slides coming along, okay? So we'll describe the cell structure, we'll talk about electrode balancing, we'll talk about the electrode capacity per unit area, we'll talk about the capacity per unit volume of the cell, we'll talk about irreversible capacity, we'll talk about jelly roll volume, and then we'll talk about omitted items. So this is the basics of a lithium-ion cell. It's a stack, okay? So this stack has a separator, then a negative electrode, which is graphite coated on both sides of a copper foil, another separator, and then 2 positive electrodes coated on both sides of an aluminum foil. And this stack is wound up into a spiral in a cylindrical cell, or in a stack pouch design. You just stack these things on top of each other, one after the other. In the pouch cells we use in our laboratory, this electrode stack, a long stack, is wound up into a flat winding. But anyway, this is the stack that's wound. And what we have to do here is figure out, if we know the characteristics of the positive electrode, for example, how thick it is, what the mass per unit area is, what the specific capacity of the positive electrode material is. If we know all these things, how do we figure out what type of a graphite electrode should we put next to it so that the cell is balanced? Okay, so I want to talk about what balance means. I'll do that on my document camera in just a second, okay? But what I want to show you is that the stack has some thickness that we call T-stack, and that's going to be appearing throughout this PowerPoint. The thickness of the stack, you just add up these different thicknesses. So I talk about the thickness of the positive, the thickness of the aluminum, the thickness of the separator, thickness of the negative, thickness of the copper. And it's pretty obvious if you can add what the thickness of the stack should be. Twice the thickness of positive, negative, and separator, because there's 2 of those in the stack, plus the thickness of the aluminum, plus the thickness of the copper. So now let's talk about cell balancing on my document camera. So let's try to get the document camera. Oh my, how do we do that again? Okay, so there's the document camera. I hope you can see it. Is it true?
Yep.
Yes.
So we're going to plot the voltage of the positive electrode and the negative electrode versus lithium metal. So that's 0 down here. And we'll go up to 4.5 volts at the top. So what happens is you start with a graphite electrode, it's up around 2.5 volts. And you start with a positive electrode, it's around 3 volts or so. And then you charge the cell. So the positive electrode goes up in voltage, and it reaches the upper cutoff that you want to go to. And the negative electrode goes down in voltage, and when the positive electrode reaches the top, as far as it goes, you want the graphite to be basically filled at that point. If the capacity of the graphite is smaller, for example, if the graphite terminated where my pen is at this exact second, and you continue to charge the cell, you would electroplate lithium on the surface of the graphite, which you don't want to do. Okay. Then when you discharge the cell, the positive will discharge, come back to some point, almost the whole way, and the graphite will come back almost the whole way as well. But there's always some irreversible capacity, and we call this Q irreversible. And this is because some of the lithium atoms that went into the graphite didn't actually go into the graphite. They ended up reacting with electrolyte components to make the solid electrolyte interface. So you believe that all this capacity that you added to the graphite was intercalated lithium, but it's wrong. Some of that lithium ended up in SEI products. So when you try to remove the lithium, you can get all the lithium out of the graphite, but not from the SEI. Okay. So when you're making a cell, a lithium ion cell, you talk about balance. And what you mean is that the capacity at the top of charge of the positive and the capacity when the graphite is full, they should match. Positive and negative capacities match for a balanced cell. The place they match is on the very first charge of the cell, right there. It's common to leave some excess graphite in the cell. We do that. Everyone does that. And that's called the N to P ratio. For a perfectly balanced cell, N to P equals 1. Perfect balance. Commonly, N to P is between 1.05, maybe up to 1.15, depending on the cell design. But what we're going to do today is we're going to work out what happens when the N to P ratio is exactly 1. So does anyone have any questions about balancing cells?
I do, actually. So this is, how does this change with different rates? So say you were to run it at, C over 5 versus at a rate of C. How does that increase the QIR? Because from my understanding, it would, but how does that fit this framework?
Okay, so this is what happens during the very first charge of the lithium-ion cell. So this is what's called the formation cycle, and this is done at the manufacturer. And there, the formation cycle is usually done at elevated temperature and under a relatively moderate charging rate, because you want the positive electrode to be in equilibrium at the voltage to which you're going, and you want the graphite to be in equilibrium at the voltage to where you're going. So typical formations are not done at C rate. Although I will tell you, in some companies, formations are done at C rate, and I was shocked when I saw that happening. But they were also done at 70 degrees C, where the diffusion rates in the electrolyte and the electrode particles are very high. So even at C rate, you could be close to equilibrium. The reason they were formed at C rate is because you could pack a lot more, you could pass a lot more cells through the formation equipment per unit time, and hence lower the capex of your factory. That was done at ATL, a big Chinese manufacturer of cell phone cells. It's crazy.
Thank you. That makes sense. Thank you.
Yeah. Okay, any other questions? Yeah.
For the irreversible capacity loss, you just label it on the graphite anode side, but does the cathode side also has a very thin layer of cathode electrolyte interface that goes into this irreversible capacity?
Normally, the cathode irreversible capacity is less than the negative irreversible capacity. For example, if this is LCO, the irreversible capacity is very small on the positive side. Or if it's LFP, the irreversible capacity on the positive side is very small. So what affects the capacity of the overall lithium-ion cell, the overall capacity of the lithium-ion cell will be this. Okay.
Okay, thanks. So it's determined by it's mainly determined by the anode.
Well, there are certain positive electrode materials that have lots of irreversible capacity, and in that case, the positive will determine. But in this little treatment, we're taking the situation where the positive irreversible capacity is less than the negative.
Okay, thank you.
Okay, any more questions about this? Okay, hearing none, I'll go back to the PowerPoint. Where was I here? Okay, can you see my PowerPoint again?
Yes.
Thank you. Okay, so the first thing we have to figure out is what is the mass per unit area of the positive electrode material. So I call this sigma P. So this is the loading of the positive electrode material. So let's figure this out. So the mass per unit volume will be the loading divided by the thickness. If you think about the area, about the units, mass per unit area is mass per square centimeter, and divide by thickness in centimeters, you get mass per cc. So what's the mass per unit volume? Well, that's easy to figure out. It's the mass per unit volume. Mass per unit volume is density. So we need the average density of the positive electrode material. It's the crystalline density of the positive electrode material, rho P, times the weight fraction of positive electrode material, WP, plus the density of the binder times the weight fraction of the binder, plus the density of the carbon black times the weight fraction of the carbon black. And then all of this is multiplied by the solids fraction of the electrode. You have to take 1 minus the porosity and multiply it by this. And that gives you the mass per unit volume. The electrode porosity today is usually about 20 to 25%. So this phi would be something like 0.2 typically. And that gives you the mass per unit volume. And if you want the mass per unit area, you would just multiply this thing by the thickness of the positive electrode. So typically these numbers, densities for lithium cobalt oxide, you should have worked that out in homework 1. If you didn't get 5.08, you did it wrong, and so on. The density of the binder is given, the density of the carbon is given, the weight fraction of the positive between 95 and 97%, weight fraction of binder, weight fraction of carbon. So all these numbers that you need in this expression are known. And then you do the same thing for the negative electrode. Same exact thing. You want to know the mass per unit area of the negative electrode? You work out the mass per unit volume. Same thing. Density of the negative electrode material times the weight fraction of the negative electrode material, density of the binder, weight fraction binder, density of carbon, weight fraction carbon, multiplied by 1 minus porosity. And all these things are known. Density of graphite's 2.2, binders 1.4 to 1.7, carbon blacks, weight fraction, everything is known, okay? So if you want to know the mass per unit area, take the mass per unit volume and multiply by the thickness of the negative, and you get the mass per unit area. Then you need to know the capacity per unit area of the positive electrode material on one side, because the capacity per unit area of the negative has to match this. Okay, they have to match each other to have a balanced cell. So the capacity per unit area of the positive side is the mass per unit area times the weight fraction of active material times the specific capacity of the positive electrode material to the specified upper cutoff. So we can calculate sigma p from what we learned earlier. The weight fraction of the positive is something like 96%, and the specific capacities for common electrode materials are given here. So, a typical electrode design, we can calculate the capacity per unit area of the positive electrode material. No problem. And what's the capacity per unit area of the negative electrode material? It's the same formula, the weight per unit area of the negative times the weight fraction of the active material times the specific discharge capacity of the negative electrode material to near 0 volts. Okay, so what do we use for the first discharge capacity of the negative electrode material? If you have a good graphite with a probability for turbostratic misalignment that's about 0.05, it will have a reversible capacity of about 360 milliamp hours per gram, and it'll have an irreversible capacity of about 10%. So roughly, the first lithiation capacity will be about 390, 360 for intercalation, and 10% getting wasted forming an SEI layer. So the first lithiation capacity will be about 390. So that's what you'll pick for your QN typically. And it varies a bit from graphite to graphite. We might have a artificial graphite where this number is 345 and the irreversible fraction might only be 5%. So you would make adjustments to this number. Okay, so I see we've reached the end of our time. So I'm going to stop here. And when we come back next time, I will briefly review starting from this point, just so that we can remember what we're doing and get to this point. So I'll do that very quickly. You know, it may be useful for you to have these quantities that are being defined here handy as we talk, because you'll see these pop up again. You'll say, geez, I don't remember what this is. So you might want to print these few pages where these things are defined. Okay, so I don't think it will take all of Monday to finish this particular part of the lecture. We'll take about half of the lecture. So I'll send you the next batch of notes as well over the weekend. And any questions before we end for today?